Hi, everybody. Welcome to the second webinar of TFTC General Webinar Series. It's been a long time we offered a webinar, so I hope everybody was doing well and had some rest from the start of the summer. Now, I am really happy to introduce today's speaker, Dr. Anshuman Sharma. Today, he will share his research about assessing traffic disturbance, efficiency, and safety of the mixed traffic flow of connected vehicles and traditional vehicles by considering human factors. Anshuman Sharma is a CV Raman postdoctoral fellow at Center for Infrastructure Sustainable Transportation and Urban Planning in Indian Institute of Science located in Bangalore, India. His research interests lie primarily in the areas of intelligent transportation systems, including connected and automated vehicles, traffic flow modeling, and human factors in traffic. He is the recipient of the prestigious Conrad Award, which is TRB 2019 Young First Author Best Paper Award in Operations section. So with all this said, let's now welcome Dr. Anshuman Sharma to start his presentation. Dr. Sharma, now the floor is yours.
Thank you so much. So first of all, thank you everyone for joining. I would like to thank Lee and Professor Chen for doing all the arrangements. I hope everyone can see my screen and hear my audio. I'll just switch off my video for the presentation purpose, so to allow good connectivity, and then during question and answer round, I'll just switch it off. Okay. So the title of today's talk is Assessing Traffic Disturbance, Efficiency and Safety of the Mixed Traffic Flow of Connected Vehicles and Traditional Vehicles. And the focus is on human factors. The contents of today's presentation is just three. I'll start with my brief biography, moving into research challenge, and then discussing about one of my ongoing research projects. So, as Lee said, currently I'm a CV Raman Fellow at ISC Bangalore, India. Previously, I was a postdoctoral fellow at University of Queensland. I was also a traffic engineering and operations advisor for AMAC Group. It's a startup coming up in Australia. And I was also a visiting fellow at Queensland University of Technology. I did my PhD from the University of Queensland. Did my master's from IIT Roorkee, India, and did my bachelor's from Government Engineering College, Bhopal, India. My research areas primarily involve traffic flow theory and human factors, ITS, and basically applying the concepts of traffic flow theory and modeling and human factors and trying to understand the emerging vehicle technology and transport. Moving on to today's topic. So basically, as you know, connected vehicles are coming, and within a foreseeable future, they have to coexist with traditional vehicles. So it's important to understand that when we have this mixed traffic condition, how that affects the efficiency, safety, traffic disturbance in general. So the major research gap and limitation at that time when we were doing this research was the models which were utilized to simulate the connected behavior, they did not consider human factors. So here, connected vehicles are defined as vehicles capable of communicating with other vehicles, but the control is still in the hand of driver. So let's say if I'm giving an information to driver, it's up to him or her how he or she reacts to that information. Let's say if I ask the driver to decelerate, it's up to him whether he decelerates or not, or how much he decelerates. So whenever we are trying to model the behavior of connected vehicles, it is important to consider these aspects of human behavior. Also, if you look into the previous studies, they overlooked how connected vehicles are distributed in the platoon. So let's say if I want to understand if I increase the penetration rate of connected vehicles within my traffic stream, how that affects the efficiency and safety of the traffic. An important point to note there is how my connected vehicles are distributed within that stream. Are they at behind or are they at the front? because the distribution of connected vehicles among the stream will also have an impact on the traffic efficiency or safety or any other measure. Okay. So one of the critical human factors for connected vehicle modeling is driver compliance. Why it is critical? The example which is shown on the screen, let's say we give an advice to the driver that a pedestrian is ahead. Now it's up to the driver whether he accepts that advice or he decelerates at that particular time or he decelerates a bit later. It's up to driver's compliance. So driver compliance became an important factor for the success of connected vehicle technology, because if I have given one message and if a driver decides to ignore that message completely, all the advantages of connected vehicle technology that we can think of will be nullified. So what I did in one of the previous studies, I have integrated connected vehicle driving strategy with intelligent driver model. So what is connected vehicle driving strategy? Connected vehicle driving strategy guides you, let's say, for example, if we give different kind of information to drivers, how we can include driver compliance in the modeling framework. So let's say there is a continuous information. By continuous information, I mean the information is available all the time. Let's say, for example, the speed of the lead vehicle or the distance to the lead vehicle. So this kind of information will be continuously available to the driver. Other part could be the on-time event triggered information. Let's say if something happens, then only we are giving the information. For example, if leader brakes hard, we are giving that information only at that particular time. So these are on-time event triggered information. So what CVDS does is, I have divided the CVDS into two parts, part 1 and part 2. Part 1 takes care of this continuous information, let's say, for example, speed or spacing. Part 2 takes care of on-time event triggered or advanced event triggered information and how driver compliance can be incorporated. So I'm not going into details about this model because because I'm not focusing on this particular study here, but one can go back to the study and just can see the study for more details. So driver compliance in that study I have modeled as using prospect theory. I've assumed compliance as a function, as a product of usefulness and weight. For usefulness, I had one usefulness function that takes care of the observed headway into account. And for weight, I have this probability function that takes care of probability. Okay. And compliance, I had divided into two parts: low compliance and high compliance. By low compliance, sorry. Okay. So by low compliance, I mean that let's say if I given a message, let's say hard deceleration, then driver may decelerate after some time or may decelerate to a particular extent, may not decelerate hard. By high compliance here, I mean driver may decelerate and driver will decelerate as soon as you give the message, driver decelerate. So that's how I'm classifying as high compliance. And so you calculate the utility of both low compliance and high compliance, and then you get the maximum utility out of it. So in this study, I have used this model to mimic the behavior of connected vehicles. And for traditional vehicles, I have used the IDM with errors. Now, what I've done is I have calculated different measures, let's say for traffic disturbance, for traffic safety, and for traffic efficiency. For traffic disturbance, I focused on oscillation duration and oscillation amplitude. So one can say the oscillation amplitude is difference between, if you take the deceleration phase, then difference between the two speeds will give me the oscillation amplitude. I have also taken two safety indicators. One is modified time to collision, another one is deceleration rate to avoid crash. So MTTC takes into account the relative speeds, difference in the acceleration values of the follower and the leader, and the spacing. Whereas deceleration rate to avoid crash takes care of the relative speed as the spacing. Then I've also measured average flow, average speed, and average density. These are my traffic efficiency indicators here. And I have used at least generalized definitions to calculate my Q, K, and B. Now, in this, I have also considered 3 platoon policies. I'll explain these platoon policies in upcoming slides as well. As I said previously, one of the gap was how my connected vehicles are distributed in the traffic stream. So I've used a best spatial arrangement. By best spatial arrangement, I mean, if I distribute my connected vehicles, so this arrangement means I have to distribute my connected vehicles in such a way that I achieve the maximum benefits from them, from their arrangement. Worst spatial arrangement means I have to distribute my connected vehicles in a traffic stream in such a way that uh, they do not give any benefits to you. And then the random spatial arrangement. It means that they are distributed in the traffic stream randomly. So here's some description about the simulation experiment. There were 2 simulation experiments. In experiment 1, I have taken 2 composition, homogeneous and heterogeneous. Here heterogeneous means mix of traditional vehicles and connected vehicle high compliance drivers, connected vehicle low compliance drivers. In homogeneous, I have taken all traditional vehicles, all connected vehicles high compliance, and all connected vehicles low compliance. Then penetration rate. So I have varied my penetration rate from 0 to 100%. Then platoon policy. In each of the experiment, I have platoon policy as my best spatial arrangement, worst, and random, both. Then there's some specific leader speed profile I have done. I have provided to the experiment. So as you can see that somewhere around 90 seconds down the line, the driver decelerates. Somewhere around 80 seconds, the driver decelerates and comes to a halt. The leader decelerates and comes to a halt and then accelerates again. So this kind of leader speed profile I have adopted so as to measure the impact of the stop and go phenomena and to see how this affects my traffic flow disturbance and traffic safety. Now, to further focus on the efficiency part, I have taken another leader speed profile where I have intentionally asked my leader to stop for a while so that we can clearly see the impact of this stop and go phenomena on the efficiency. One point to note here is that I have only considered a single lane scenario here. Yes. So if I focus on the comparison of platoon policies, here you can see worst case and best case scenario. So in the worst case scenario, I have arranged my connected vehicle such a way that there is one traditional vehicle in between 2 connected vehicles. So just one more thing I need to point out here, that is the assumptions I have made about my connected vehicle. So let's say this is one connected vehicle and this is another connected vehicle. Pardon me for my drawing. So that's my one connected vehicle and another connected vehicle. So they will communicate with each other only through communication. So I'm assuming that the connected vehicles do not have the capability of sensors here. Okay. I'm assuming that they only communicate with to various communication like DSRC and all. Another important thing is a connected vehicle will benefit from the information only when connected vehicle is in front. Another connected vehicle is in front because of the kind of information I'm providing. Let's say, for example, I am focusing only on the speed of my leader. Now, there may be a second leader, which is also a connected vehicle. Now, if I want to pass this information to this particular follower, then I have to think how the human driver will differentiate between the speed of first leader with speed of the second leader, right? How we'll communicate this scenario. So because of that, whenever a connected vehicle is ahead, then only my follower will be benefiting from the information. Okay. So if I want to simulate a case of worst case, what I'm doing is I'm putting a traditional vehicles between 2 connected vehicles. So as soon as I do that, and whatever information I'm passing from here to here, it's not much of a use for human driver because he cannot differentiate whether that information is for the leader ahead or for the second leader or something like that. Similarly for the vehicles which are behind. So in this way, I have simulated my best case. So when you have a best case scenario, you can see that because of leaders stopping and accelerating, this congestion is penetrating down the street, right, till the end of this platoon. But here, as soon as I arrange my connected vehicles in the best case, by best case, I mean I'm putting all my connected vehicles in the front of the platoon. So when I'm putting all of my connected vehicles in the front of my platoon, they are able to bear the negative impact of this deceleration, stop position, and then acceleration. Okay. So these are the results of experiment 1. So you have all traditional vehicles, all connected vehicles, low compliance drivers, and all connected vehicles, high compliance drivers. So all traditional vehicles, you can see the congestion is penetrating till the end of the platoon. All connected vehicles, low compliance drivers, it penetrates, but then it diminishes after some distance in time. And here in connected vehicle high compliance driver, the negative effects diminishes quite soon as compared to the low compliance. Moving on. If I focus on experiment 2, where I've asked my leader to stop twice so as to build a congestion up to a very high level, you can see the impact on all traditional vehicles, then connected vehicle low compliance, which is better than traditional vehicles, and connected vehicle high compliance, which is again better than both low compliance and all traditional vehicle case. Now, moving on. So now here I'm focusing on the mixed traffic of connected vehicle high compliance and traditional vehicles. And let's say first is traffic disturbance. So if you focus on average amplitude, what you see here is in the best case, the average amplitude reduces when the penetration is somewhere around 20, and then it basically remains at that point. But if you focus on the worst case, where I have arranged connectivity in such a way so that their benefits reduces, what happens is till up to somewhere around 50% of penetration, you don't see much benefits because intentionally I have arranged them in the worst case. So what it shows is in the traffic scheme, if we do not have any control on connected vehicles and the way I have defined them, what happens is even if you increase their penetration rate, you may not see many benefits. On the other hand, if you see a random case, so one point I would like to highlight here is the random case. I have done simulation only 250 times. So these are the average of 250 times done random simulation. So random is somewhere in between, you can say. Now, if you focus on average duration, you again see the same pattern, that with the worst case scenario, for up to somewhere around 50% of the penetration, you do not see much benefits. However, in the best case scenario, you do see that after let's say 20-30%, the average duration reduces to somewhere around only 2 point or somewhere around 3 seconds. Now moving on to the traffic safety measure, and we see similar results for traffic safety as well. Now, if you focus on the minimum TTC, in the best case scenario, you can see minimum TTC is high, which means that it is safer, more safer. However, in case of worst case scenario, again, you see the similar pattern that after certain penetration rate, the benefits increases. However, in the random case, you can see that the benefits are increasing until 100%. Obviously, it will match the best case scenario. Similarly, for minimum DRAC, we have similar pattern and similar results. If you focus on the traffic efficiency part, where and this is only for penetration rate of 80%, you can see the difference between the best case and the worst case scenario here. I've not put random here. but you can see clear difference between the best case and worst case scenario. At a particular station location, I have just started measuring using ID's definition, the flow, the speeds, and density. Similar results you can observe for speeds and density as well. You can clearly see that you have higher flow with the best case scenario, and the flow reduces for the worst case scenario. And this is for, by the way, penetration rate of 80%. Okay, what could be some study implications? Keeping in mind how I have defined my connected vehicles, and I've done only random simulations for 250 times, we can still have some understanding of how to distribute these vehicles within the stream. So obviously in a traffic stream, and the traffic stream will benefit if you have, based on these simulations, if you have all the connected vehicles grouped together in one platoon, and we have put them intentionally ahead of the traffic stream, so that whatever there are negative impacts of deceleration or something ahead of them, they can bear it, and then they can diminish the congestion or the shock waves and all, and that will not have influence on traditional vehicles. But one thing we have to keep in mind is how CVs are defined here. I'm saying that they do not have any sensors and other things. Moving on to one of my ongoing research projects. So currently, so this is related to CAVs only. So currently what I'm working on is trying to understand if we give this real-time feedback to drivers, how that affects driver behavior in terms of response time, in terms of TTC values, in terms of MTTC values and all. So, and this is a project which is a partnership between ISC and a startup called Retradine and the government here, BMTC. And this is an on-road experiment where we have fitted devices on buses. These devices using detection and tracking algorithms, which are proprietary to Retradine, they alert the drivers about distraction, close following, hard braking, and all those things. And then we have videos and we have all the data of buses and all. And we are trying to understand using trajectories how that will impact driving behavior in terms of, let's say, response time or safety characteristics, let's say TTC or MTTC. Okay. Thank you so much. Intentionally, I kept my presentations for somewhere around 30 minutes. Thank you so much. Right. If there are any questions, I'm happy to take them.
Yeah, thank you so much for what is it? Thank you so much for your wonderful presentation. It was great time to have an insight about the effect of human factors in this mixed traffic situation. So now the floor is open to the audience. So please unmute yourself to cast a question, or feel free to leave it on the chat box also, so that we can read it out for you.
Oh, maybe I can start with one question here.
Yes.
Yes. Thank you, Anshuman. I think it's quite interesting. So I'm curious about the ongoing work that you are doing. So, so are you saying that you provide a real-time input? Let's say you tell the driver that the vehicle is braking, and then you will measure how that affects the behavior of the vehicles.
So in this particular experiment, the leader deceleration alert is not included. TTC is there.
Oh.
Time to collision warnings are there. collision in terms of collision warning is there, but not the hard deceleration of the leader.
Oh, okay. So for example, like for this bus driver, he will receive the information that, okay, the TTC from this vehicle is, let's say 1 second, from the
Yes.
other is 0.5, something like that. Oh, I see.
Only alert. So let's say, for example, they have set a threshold. Obviously, it's close to them, and their algorithm is not open. But the thing is, obviously, there's a threshold, and once it crosses that threshold, it just alerts the driver.
Oh, okay. Do you get to change the threshold and then see how that what kind of effect it will produce?
So currently, I have just analyzed the response times. Yeah, I have not gone into the. I still have to analyze for deceleration and other things. For response time, surprisingly, what we found was there was not much difference in control case and this case. So when we compared.
Oh, I think we get disconnected.
Sharma, we can't hear you. I think his connection is not very good right now.
Maybe we can wait a little bit for him to reconnect.
We can wait some moment. Oh my God.
I think he lost the connection.
Yeah, he's not in this meeting right now. So let's wait for a second for him to come again.
Yeah. Maybe we can insert a little bit here. So for the audience here, if you're interested in presenting your work, feel free to contact us. So for example, Garion or me or Hao here. I think we have almost all the slots open in the summertime. Oh, there.
Hi. Hello.
Okay, Anshuman, you're back.
There was a sudden power cut. Am I audible now?
Yeah.
Yes, hello? We can hear you.
Yeah, so what I was saying is, interestingly and surprisingly, we found that there was not much difference in response times if I compare test case and the control case. One reason could be what we are thinking is because the sample size was low. It was only 40 drivers.
Okay.
One reason could be that. Other reasons could be maybe the effectiveness of the alerts. By that I mean how we are transferring the information. So currently it is auditory based only. So because we asked them, so this is not being tested a lot. This is second or third testing of their devices. That's what our best guess is. The plan is to conduct the experiment for a large number of drivers, but these are the initial results. I still have to evaluate for their deceleration, acceleration noise, and all those measures, spacing and headways, what they are maintaining and all.
Oh, I see. Yeah, that would be very interesting.
This is a real world experiment, and we have not controlled the leaders or leader speed profile. It's just completely random and real. So in that particular case, it is important to have data from more number of drivers so that statistically we can see some difference. The response times are within the range or what we see in the literature, somewhere around, the means are somewhere around 2 to 2.5 seconds. So that makes sense. But to find some statistical significance or maybe no significance, we have to have we should wait for at least somewhere around 80 to 100 drivers, because we are not controlling leaders, or we are not controlling any traffic ahead.
I see. Yeah, I think that would be very interesting. I'm very curious about the results. Maybe we'll bring it back once you have the analysis ready.
Sure, definitely. We plan to submit one at TRB, so let's see.
Okay, we will book you for the next webinar for that one. Okay, yeah, let me save the time for other friends here to ask questions.
Maybe I can follow up with a question. First of all, thank you for the presentation, especially at this time over there.
Yes.
So I guess you can't show the slides anymore, right? But
I
when
can
you
share
show-
slides. I can try.
Oh, okay. 17 or so. This is where you show the, what you call the worst case, I guess. So the point I wanted to make is that, so from the figure, yeah, those types of figure. So if you compare the delay, the total delay on vehicles, it's probably going to be 0, right?
If I compare the delays
Yeah.
to reach, no, because here this is the stopped, they are stopping here. Okay. So if I compare the total delay and to cover that particular stretch, I think in the best case scenario,
So
delay will be
just consider the delay in the system. So on the whole link in this case of all the vehicles, right? Which is what we care when we do planning, right? We want to minimize the total delay.
Yes.
Yes. So that delay should be 0 or not. I mean, the difference in the total delay between the two.
Look, so in the worst case scenario, they will stop for some time, right?
Yeah, but the delay is not the time you stop. The delay
Correct.
is the travel time compared to the free flow travel time. Right?
Right. So yeah, at the moment here, we did not consider that, but yeah, that could be one of the metrics that we can look and we can analyze. But the only thing is, this is single lane. It's not at the network level. Only single lane scenario for a stretch of around somewhere around.
But if on a link, you don't have a benefit on the network, you won't either, right? So it's good to start with the simplest cases.
Correct.
But the point I'm making is that the delay in these cases is going to be the same. So you shouldn't expect the benefit from delay. Maybe there's a benefit from emissions, right? Because vehicles are not stopping, and that's potentially good, right? But from a delay perspective, it's important to make the point that one shouldn't expect benefits.
Yes, I agree. But we can also look into the safety aspect. It's not only the
yes.
If you look at the safety aspect, then you can say in the best case scenario, the decelerations and the MTTCs are quite good.
Right.
However, in the worst case scenario, they are quite low. So if we have not considered delay here, but if there's you have to draw an overall picture comparing safety measures, efficiency, as well as the disturbances, I'll still say that the best case scenario may perform better.
Very good.
Actually, related to that, I have a question. So Ashma, can you show your slide 19? Yeah, the simulated results for A is quite interesting. Why they go that way? For example, you see some short waves in certain speed, but some others going this way.
So you are saying for this one?
Yeah, yes. Can you see my drawing?
Yes, I can see your drawing. Yeah.
Yeah.
Actually, it is first is here the heterogeneity in the driver behavior I have not considered. So they all are homogeneous drivers with the same set of parameters for the IDM.
Yeah, so here, based on the result, it is saying that you have different short waves there. Some are propagating at a smaller speed, some are at a larger speed.
Correct. Yes.
Oh, that's very interesting.
I guess that depends on the parameters you use in IDM. Sometimes you get strange results like that.
So you think it's because, like, for example, here, because those parameters are not string stable, so it generates additional disturbances there?
Quite possible, yes.
Very interesting.
That's why one should use Newell's model.
Then you don't see the amplification. Then it's all identical.
Yes.
But here I'm curious, Anshuman, so what did you, here you see that the CV, it has the benefits of dampening the disturbances, right? So what kind of behavior did you assume that they can reduce the
the time headway, if the time gap parameter, if I specifically can point out an IDM, so that time gap parameter, time gap is larger for low compliance and high compliance drivers. So because the time gap is large, that's one of the reasons why they are able to diminish the effect of these two decelerations.
Oh, I see. But then it means that their throughput will be smaller, right? Because you have a larger time gap.
Correct. So what if you kind of measure the flows and flows and the speed in this initial part here, I don't know whether you can see my cursor here. So there, if you measure, obviously the flow will be better here. However, if you focus on the congestion scenario and overall, then what happens is it is better for high compliance and low compliance.
Well, but yeah, the same point remains. I mean, if you look at the delay, the bottom one is clearly worse. I mean, you can see a lot more green, right? The platoon is a lot broader. So
something is funny in that.
Yeah, so you can always find, localized measures that would make some schemes look better than others. But if you look at the whole thing, which is the way we should do it, right? We would find opposite results in many cases.
But here I don't understand why here you see a lot of green at lower speed. They don't recover.
Where?
Here, maybe I should change another color. Here, so after the disturbance, it seems that they do not recover to the free flow condition.
They take longer maybe to recover, right? Yeah.
Yeah, maybe longer.
Cut it somewhere around 1.9 for all. Okay, so maybe they are taking a bit longer to recover, but I should have cut it in a better way so as to better represent them. That's the only thing.
But that's also very interesting. So it means that you can see some other effects.
Yes, focusing on the recovery part. Yes, comparing the recovery part can reveal some more interesting things. Yes.
Yeah, it is.
So that's going to be due to the prospect theory model then? Is that the only difference between humans and connected?
Yes.
Yeah.
I have a question for you with this scenario with only TVs and CVs with penetration rate of 50%. Like the first graph, like it was, I don't remember what the slide number was, but I think it was 17. Yeah, with your
Penetration rate 80. Okay.
Okay, like with your assumption that CV will behave like CV only when another CV is in front of CV, why is the
Yes.
best? Yeah, why is the best case scenario putting all CVs in the front? Because I am curious that like two CVs to communicate each other, and then two human vehicles follow, and then two CVs and two human vehicles, and so on, will behave better because like CVs can suppress the stop and go wave of human vehicles. However, in my thought, if we put all human vehicles at the end, they will generate oscillation anyway. Like, have you ever tried another option? Could be the better, like special, best.
Yes.
best
So if I
special-
talk about, yeah, so if I talk about it, if we put all the human drivers at the back of the platoon, what happens is the CVs were able to decrease the shock as compared, decrease the shock soon, so that that shock is not transferred to human drivers. Okay, now when it comes to the case why, so I'll come to two CVs and two TVs part. But first is why two CVs together? Because I've assumed that there's only communication. And second thing, what information can we give for from third CV to the follower? How you will differentiate that information for the human driver? How he will differentiate or she will differentiate? Okay, this information is from the vehicle ahead, or this information is the vehicle second vehicle. So we need to do some experiments on that to see, okay, how we can communicate that information. When it comes to two CVs and two TVs, if two CVs were able to bear all the effect of these shocks, then we can say yes, there could be more benefits. But because depending on the type of regressive effect of the leader on the followers, that will affect. Let's say, for example, if there is the like continuous stop and go phenomena happening, and what happens is you will require more than two CVs to bear it, or maybe some X number of CVs to bear it. Yes, but let's say, for example, if you have 50 connected vehicles and 50 traditional vehicles and then 50 connected vehicles, in that particular case, we may find that what to say, that metric, that okay, we can keep 10 or 12 first, then 10 or 12 later, and then followed by 10, 12 connected vehicles. But we have not gone till that point.
Great. Okay. Thank you for your answers. Are there any more questions from the audience?
Based on that last question, are you having any plans to do a sensitivity analysis to determine the threshold for speed harmonization with respect to the number of CV vehicles needed to smooth out the traffic?
Yeah, it is in the plan, but at the
No,
moment,
I'm just looking forward to, if it's, something you can present on later, that's all.
It's definitely in the plan. Yeah.
Great, thank you.
If there is no question from the audience, are there any? Then I think it's perfect time to end today's webinar. Again, thank you so much, Dr. Sharma, for being with us today. And thank you to all the participants joining us. We really look forward to see you again in following webinars. The webinars will be announced at Google Groups as usual. And as Dr. Chen mentioned, if you want to contribute to a talk, please contact us through Google Groups or my LinkedIn, or yeah. So wish all you have a nice weekend, and thank you.
Thank you everyone.
Thank you for your great presentation.
All right, thank you, everyone. Thank you, the presenter and Young, for organizing this.
Thank you.
We should mention that we also promote this on Twitter now. So if you have a Twitter, keep an eye on that.
Great.
Okay.
Thank you.
All right.
Bye-bye.
Well, thanks a lot, Anshuman.
Thank you, Professor. Thank you.